see. All right. Let's get started. Does anyone have any questions? No? This last few sections, they are quite mathematical compared to a lot of the things that we have done before. And what you see is that, I mean, as I mentioned at the start of this chapter about 2 weeks ago now, fluid mechanics or continuum mechanics more appropriately is a very big field in itself, and you can take several courses on it if you want. And it is very important in many different ways depending on what you study. And it's quite a different approach in both techniques and phenomenon compared to traditional standard physics that you do. In intro, you see just a tiny little bit of it in terms of the bulk, the different moduli like Young's modulus and bulk modulus, shear modulus. But beyond that, you don't really do anything. So one of the things, I mean, the part of the reason to do this is just to expose you to it, and we don't have the time to do it justice. But whatever the case is, we defined the stress tensor the other day, and because in continuum mechanics, what you always do is you always have some finite body, and you can wash away the graininess and treat that object as a continuum. So a lot of quantum mechanics is not in here, or rather they're not important, right? And you can approximate everything as if it's made up of a continuum. So we typically would talk about, so when you describe anything, you always have a coordinate system, right? And you have an origin. And so whatever the solid or liquid is, or the fluid is, when you consider continuum, you always look at an element of volume. So if you want to think in terms of Cartesian coordinates, that's what you would have. So your dV is dx, dy, dz, if you want, right? Product of all of these infinitesimals. And typically you think of the position either to the corner or to the center of the elements of volume, doesn't really matter. Okay, so you describe it in terms of its position. Now, since we're interested in distortions in motion, right, especially in distortions, then what we are thinking of is there's some equilibrium configuration, right? And then distortion is, if the equilibrium configuration or the equilibrium position is given by R, then what is the distortion? Then it goes to R plus du, I think is what, plus u. This would depend on R and possibly time. It should depend on time if it is time dependent. And you can think of this R as either the equilibrium position or the position at some time t naught that you pick. Okay, so the picture that you might have would then be after the distortion, it moves to something like this. So this is R plus U. Okay, this would be how we would describe U. Now, if you think about it, let's just take this point R. And you think of some neighboring point dr, then if this point R is distorted by adding U, what was the question now? It just pops up and I don't see it.
Oh, I thought you meant the R plus DU.
No, yeah, okay. Let me see. Let me change that so it doesn't look like a long X. This is highly exaggerated. Okay, so this is at the point R, you distort it to this point, to this point over here. All right, then the neighboring point at R plus dr might be distorted to this point. So let me just ignore the time dependence. And this would become U of R plus dr. So if you ask, what is actually this displacement? See, originally in its equilibrium configuration, these are the two neighboring points. After the distortion, what does it become? It becomes this. So before that, it was separated by dr. What is this? Now, if you work it out, you can see that this is just dr plus du. Right? It's easy because it's just vectors. This vector is this vector plus this vector plus this vector. So this is minus u plus dr plus u of r plus dr. And so u of r plus dr minus u plus dr. And this is du. So you can see why that's the case. But on the other hand, you know that given any function u that has x, y, z components, then the ith component is by definition partial u sub I by partial, your book uses the notation r sub j, and then dr sub j sum over j, j from 1 to 3 if you want. All right. So in general, what you can write is, you say, what is the vector du? This is going to be equal to, and in fact, what you find is that you can write it in terms of a 3 by 3 matrix. And looking at this expression, you see, this is the one component, the x component, the one component of the partial u sub x by partial x times by dx, partial u sub x by partial y times dy, and so on and so forth. If you look at that expression, then you can see that this is a matrix of partial derivatives, which is partial U1 by partial R1, partial U1 by partial R2, and so on and so forth. This is partial U2 by partial R1. And you have a third line, a third level here. Okay, now, if you look at this, you might think that this is a way to define the stress. I mean, sorry, the strain. The strain is the change in the position of the object when you distort it, right? But if you think about it, you don't have to discount pure translation, because if you have pure translation, you are not distorting the body at all. And you also have to discount pure rotation, because once again, if you purely rigidly rotate the body, the whole body, every point is rotated, then there's no distortion either. So you don't need stress to bring about any of these strains, right? If you rotate the object, you're not applying any internal stresses, any internal force to the system. Also, incidentally, because a fluid can distort, you can change its volume without applying stress. The description that we have pertains only to a solid, and we'll only be looking at solid. Fluids don't have time to look into it. But anyway, so to discount translation is easy, because if it is pure translation, du is just a constant, right? Constant vector. So if you, u is just a constant vector. So if you take this matrix of partial derivative, it's all zero. So it doesn't matter whether you translate or not. Du would automatically not worry about it. It doesn't care about it. However, that's not true of rotation. All right. In rotation, you find that partial u, the matrix of partial u by partial r, is not going to be equal to zero. So the first thing that the author did is to discuss for small strains. That means for small distortions, right? What happens if you have small distortion? That means your matrix of partial derivative, your 3x3 matrix, is actually consists of small numbers. So they first look at rotation. What if you have a pure rotation? We learned from before that a rotation can be defined by this vector, which is the angle theta that you rotate through in the right-hand rule sense, right? You turn the screw in the right-hand rule sense, but what direction? In the direction may be denoted by, the book uses u hat. So if this is u hat and you rotate it the right-hand rule way, so you turn the screw in the advancement of u by an angle theta, this would be small. All right. Then you can ask, what is my matrix of derivative, partial derivative? So in order to do that, basically, I've got to figure out what u is, because this is going to be equal to this matrix of partial derivative times by dr. All right, so if I can figure out for a given distortion, rotation in this case, what the changes du are, then I can figure it out. So given this, for pure rotation, you find that the displacement in the body is going to be equal to the velocity times by time dt. So if you turn at some constant rate, right, the velocity is going to be given by v dt, with v, because it's a rotation, given by omega cross r. So if you were to work this thing out, you can get u equal to theta, cross r. And when you do this, then you can easily work out what the matrix of partial derivatives would be. Okay, now in doing so, you will find that, this is a cross product. So you have E1, E2, E3, theta 1, theta 2, theta 3. Those are the XYZ components of theta, right? And then you've got XYZ if you want. So you take this, you would know what u sub x, u sub y, u sub z is, and d would be partial ux by partial x. Sorry, x and partial ux by partial z, and so on and so forth. And if you were to do this, well, I've done this several times, and what I end up with is a matrix that is different than what is in the book by an overall sign. That's what I get. The book has the signs that are like that. Oops, I don't understand why they have that, but whatever the case is, it doesn't matter. What you find is that this partial matrix, partial derivative matrix, is what we call an anti-symmetric matrix. And so because of that, you find that there is a way to take into account distortions that correspond to pure rotation. So in other words, if you can give me U, I can form D, okay? But I don't want to worry about motion of the body that is a result of rotation. So I've got to take it out. And apparently, if you look at the thing, you will understand that given any matrix D, you can always write it as D plus D tilde plus 1/2 D minus D tilde. All right, if you remove the parentheses, you would see that. And D tilde is just a transpose. And then, of course, you would see that the way it is written up now, one part of it is what we call a symmetric matrix. And that's because this is symmetric, right? Because if you if you take the transpose of d plus d tilde, it goes to d tilde plus d, which is itself. Whereas this is the anti-symmetric part. Because if you go d minus d tilde, if you take the transpose of it, you get d tilde minus d, which is exactly the negative of this. So you know this is an anti-symmetric part. So now you know how to discount rotation. If you give me the matrix of partial derivative, I just take the transpose of it, add it to the matrix, and divide by 2. So in other words, this is the definition of the so-called symmetric, the so-called stress strain tensor. I think they give it the symbol, doesn't matter. Okay. E is 1/2 d plus d tilde. So this is the partial derivative matrix D, and you take the transpose of it, you add it to the original, divide by 2. That's how you define the strain tensor. And you can actually look at examples 16.5 and 16.6 to figure out what the different parts of the, where is it now? Yeah, what the elements of the strain tensor represent, like the diagonal terms would correspond to stretching along the I-th axis, and the off-diagonal terms correspond to shear. That's the shearing strain, in other words. That's actually the result of 16.6. Anyway, there's a lot of this. There's a part after this that talks about how you can decompose a given strain tensor into a part that is basically the unit tensor plus another part that they call the strain deviator. That's because it deviates from this. Now, example 16.5 shows you that if you have this kind of strain, all it is what they call a spherical strain. So you either expand uniformly, so you blow up the sphere, so you expand uniformly in all directions, or you contract uniformly in all directions. Right? But this actually is fairly straightforward. The reason they do this is so that this part of it, because it involves the diagonal elements of E, which we just went through, is the part that corresponds to the strain along the axis. So you either stretch along the axis or you contract along the axis. And the way that they define E as 1/3 the trace of the strain tensor means that the change in volume due to this part is equal to the change in volume of the original strain. So this is pure shear, got nothing to do with the part that changes the volume anymore. Anyway, the reason they go into that is in the next section when they talk about Hooke's law. Hooke's law, or the generalized Hooke's law, is to try to relate the the stress and strain tensors. So recall this, all right? Your stress tensor, which is a surface thing, is a function of the surface area, is equal to the stress tensor multiplied by dA, and the strain tensor is related to the du by this relation. And what they want to do is, how is stress related to strain? Okay. And so there are basically two, they can't solve everything. So the simplest model that they can have is, if the strains and stresses are small enough, then we expect the response to be linear. And to make life simple, we also make it rotationally invariant. So these are the assumptions. You can apply this to any solid that responds in a linear manner and that are rotational invariant. Rotational invariant means that if you rotate the system, all the responses, the stress and the strains, will all be the same. Now, this is fairly mathematical. I don't want to get into it. The conclusion is equation 1695, which relates to 1695 and 1693. So how is sigma related to E? You find that sigma is related to E in this way. And you can invert this equation to get E in terms of sigma. So that's just algebra. And E in terms of sigma would then be equal to this equation. Alpha and beta are just constants at this time. Trace of this times by the unit tensor. Now, this is ugly looking, but it turns out that if you go over the arguments, these can be related to the different moduli. We only discussed 3 moduli, bulk, shear, and Young. And it turns out that you can show this. This is done in your book. Alpha is related to the bulk modulus. Beta is related to the shear modulus. And it turns out that Young's modulus is not independent. Young's modulus is actually related to the bulk and shear modulus. This is something that can be done. It's actually a problem in the book, but I'm not going to worry about it. I just want to run through this because the details are just too much and it's going to take a lot of time. So I'm not going to worry about it. And the important thing really is what we get out of it. This is something that we can use later on to get the so-called wave equation in a solid. In other words, if I have a solid and I want to know what is the speed of a longitudinal sound wave through the medium, or if I were to strike the piece of metal, what is the speed of the wave that is set up in the metal? How would you actually do that? And it turns out that we can do that by actually looking at the equation of motion for an elastic solid. And this one has the same kind of approach that you should be used to, and that is looking at an element. So once again, right, you have your solid, you have your coordinate system, you look at an element, and if you want to describe the motion of this, of this object when it's subject to a stress and an external force for that matter, then how do you do it? Well, anytime you want to look at equations of motion, well, you either set up Lagrangians or you set up Newton's second law. And at this stage, we'll just look at Newton's second law. I wonder if advanced treatment would use Lagrangians in there. Probably they can do it. But whatever the case is, suppose you have mass density. This is mass per unit volume. All right. And you're looking at this object, and the whole volume is V, but I'm going to look at an element, dV. Because if I can look at an element, then I can hope to solve it by integrating over the whole solid. That's always the case. So if I want to apply Newton's second law, then remember that every point R under the distortion, it goes to R plus U, right? So if I look at R as the equilibrium position, then this is like I have a string, or I have a rod, or I have a bulk solid. So it's just sitting there. For a string, we can displace it in the transverse direction. We can displace it in the longitudinal direction. It's the same with a solid. So we're thinking we're going to displace the solid from its equilibrium position. In other words, U describes the displacement. So I want to know, how does the displacement, the disturbance that is set up, in other words, how does it propagate with time? What is its equation of motion? So in other words, I want to know how U moves with time. So if I displace it to a different point, right? So this is U. How is U going to respond when I let go? This is under stress and strain. Now, you strain it, you distort it by applying a stress to the system. So when you release this stress, or as the stress changes with time or whatever, how does the system respond? So you look at this element of volume and you say, by Newton's second law, its mass, you just rho dV, right, times by its acceleration. Now its acceleration is second time derivative with respect to second time derivative of the displacement. So that's the displacement. Mass times acceleration, what must it equal to? It must be equal to the net force exerted. Now, as before, we divide those forces into volume forces and surface forces. Now, the surface forces would be what is on the surface. So surface, let's say something like that. On the right surface, the top surface, all 6 surfaces, if that's my element of volume. All right. Now, for concreteness, what your book did is to write the volume gravity. So if this is subject to the force of gravity, then it will just be volume, mass, which is rho dV times by G. That will be your volume force. If you have other volume forces, you just put them in, all right? But what they are really interested in is this part, the surface part. Now, because of the elements, the surfaces are exactly what is the notation that is used now? The F of dA. All right, this is the stress tensor times by dA. Anyway, this is the force that we are talking about in here. And so if you have an element of area, then over dV, what you have to do is you've got to sum over the whole surface of the volume. So this dV that we're talking about, what is the surface force then? I'll put it here. Well, what you have to do is you've got the sum over all of it. The sum over all of it is integral sigma dA. I can't write it bold, but remember, this is a tensor. This is a 3 by 3. And so you have a tensor 3 by 3 multiplied by a vector. So this is a vector quantity. All right, so okay, so we are going to try to make sense of how would you do this? How would you, you're doing an integral over the whole box, right? The surfaces of the box. So that's what this quantity here represents, this quantity. All right, now here is where I don't want to spend the time doing it because it will be too much time. But if you use the divergence theorem, if you want to, you can write it out, right? Remember, like I said, this is a 3 by 3, so you can do it component by component. So if you want the x component, so this is the u sub x, g sub x, the x component would then be, you have a 3 by 3. So only these terms would come in, multiplied by this, right? dA as a vector, it's got the x, y, z components in there. So then you would see that you will have essentially a dot product, right? This times this plus this times this plus this times this is a dot product. And if you use the divergence theorem, you find that the divergence theorem is V, a vector dotted into dA, integrated over some surface, can be converted into a volume integral, the divergence of V dV. All right, so you can go over the mathematics of it, but ultimately the bottom line is at the end of everything, you find that the surface term, which is the integral of f of dA, which is what I've written down as the tensor sigma dA over the whole surface. If you do this conversion and you do the integral, you can do the integral because dv is small times by dv. Okay, now sometimes you may get confused. This dv is this dv. Let me go back to here. All right, it is this element that I'm talking about that we are considering. It is the same dv as this and as this. All right, but in the mathematics going to it, this dv is not this dv. This is a variable of integration. This really, when you apply the divergence theorem, this v is actually dv. All right, you are integrating over the element of volume. So in case when you're going through this and you get confused by the notation, I would have used different notation just so you don't get confused by it. But they're actually different quantities. After you go through all of this and then you ultimately get this as the equation of motion, you can get rid of all the dv's and you get this. Okay, and the this can be written in terms of the strain tensor as well as the different bulk moduli, alpha and beta. Right? Well, alpha and beta are related to the bulk and shear moduli. But anyway, and you do more math to simplify this, actually more likely to simplify this. All right, you've got to go look to see what do you mean by the divergence of a tensor. They define it for you. Anyway, then you ultimately end up with the so-called Navier equation. This is what we want to get to. This is very complicated looking. And if you ever take a course in fluid dynamics, you'll know that, well, the math is not difficult. You're not using very complicated math, but it is very tedious. Times by the gradient of the divergence plus shear modulus times by the Laplacian. Anyway, all right. So this is what we want to get to, because from here you can derive the equation of motion for a longitudinal wave and a transverse wave in a solid. Now, if you have a solid, if you want a longitudinal wave, that means whatever the solid may look like. So suppose you say, I want to create a disturbance in there, and the displacement is in the x direction. All right, so this is your u. In other words, u is simply u sub x 0, 0. U sub x is a function of x and t. All right, that's this u we're talking about. In general, it's a function of x, y, z, but since we are creating a planar disturbance, if you want, it doesn't depend on y and z. So no matter where you are in this plane, let me use a different color. All right. As long as you're in this plane, every part of this solid undergoes the same uniform translation. All right, or distortion, more like it, because it depends on x. It's not a constant, so that's not a pure translation of the whole solid. But whatever the case is, if you know this is the form of U, then you can simplify this part of the Navier equation. And when you do that, lo and behold, especially if you ignore gravity, which is what they assume here, then you will get the one-dimensional wave equation. And this one-dimensional wave equation gives you longitudinal, gives you the speed of the longitudinal wave, which is in terms of the different moduli, right? And it is now equal to bulk modulus plus 4/3 shear modulus divided by rho. And likewise, if you do a transverse wave, transverse plane wave again, transverse plane wave means that U is equal to, we are looking at propagation in the X, so we put a distortion that's transverse to it. So let's pick Y. So suppose U is equal to this, and as a plane wave, it means it's a function only of X and T. Okay? And if you were to do that, then you go to the Navier equation, you work everything out, then you also get a one-dimensional wave equation coming out, and the speed of it, it turns out, is equal to this. And this expression shows you that if you don't have, if your shear modulus is 0, then you don't have a transverse wave, right? Because if this was 0, then your speed of your wave is 0. And that is understandable and what you would expect, because shear measures how much your system distorts when you apply a force that is perpendicular, parallel to the surface. All right, whatever your surface is. So your shear force looks like this. And typically on the other face, the left face, it'll be in the opposite direction, so that the net force is 0. Your system is not moved, but it would distort. And anyway, so if you cannot sustain a shear, then you have no transverse wave. So one of the interesting thing is, and the other thing, if you note, is let me say this is longitudinal and this is transverse. Just by looking at the two expressions, you can see that the longitudinal wave is, the speed of the longitudinal wave is always greater than the speed of the transverse wave. So in earthquakes, we live in earthquake country, you find that when the earth displaces, it actually sets up two kinds of wave: the longitudinal wave that travels at the speed c sub l, and the transverse wave. And this tells you that the longitudinal wave travels faster. And so the geologists call that the primary wave. and then the secondary wave is the transverse wave. And there are different speeds. And if you can time when the transverse wave arrives versus when the longitudinal wave arrives, and you know property of the Earth, so the shear and Young and bulk moduli. And so you can then know the speeds, then you will know how far the earthquake is from where the detectors are. And another thing is for a liquid that has very, very low viscosity, or at least if your shear moduli is much smaller than your bulk moduli, then you can basically treat this to be zero. Then you will have no transverse wave. So what you find is that, how do I erase? Okay, something like this. I'm going to clear all the drawings. You find that for the Earth, how do they know that the center is actually liquid? That's because you find that when there's an earthquake there, the longitudinal wave can actually travel, but the transverse wave doesn't travel through the core of the Earth, which is liquid. So that's how they actually know the core of the Earth, or at least part of it, is liquid. Well, anyway, does anyone have any questions? Well, anyway, so the homework that the problems that are assigned up through last week, please hand them in whenever. You can hand in next week if you want. So the two problems from Tuesday, you don't have to hand in. I will write up the exam sometime by tomorrow. I'll send it to you, and you can email it to me next Friday. I know your exam is scheduled for next Thursday, but I'll accept it on Friday next week. All right, any questions? It'll be open notes, open book. Just make, yeah.
What section is the exam covering up to?
It will be from the last two chapters.
So relativity in this one?
Yes.
Okay, thanks.
Up to what we covered today. What we covered today, it's if you want to go over the derivation or to prove certain things, it's difficult. Oh, that reminds me of something. They try to sketch out the proof for what the consequence of media a system that is linear and rotationally invariant, and then argue out the form of it and whatnot. They don't even go into it. And so if you read the footnotes, they'll tell you to do it properly, you've got to look at group theory and look at some of the properties of groups and whatnot. So my point to it is, in certain parts of physics, group theory is actually quite useful. So if you are ever in a mood to take a math course and you're wondering which one you should take, group theory is one of the more useful ones, depending on what your emphasis is, of course. If you want to do something like general relativity or general field theory, then maybe topology might be more useful. So what I was saying is, yeah, the derivation part is quite mathematical, more involved, but the application of it is, I mentioned, I highlighted all the main results, just like the textbook did. So, so applications of it are fairly straightforward. So what's that question on equation 16, 117? Let me look at what 117 is. Yeah, okay. Is the last term?
Yeah, equation 16, 118, combine those two terms, but can it be combined in 16, 117 also?
You have, yeah, that's what you have to do. If you use the form of u for longitudinal and transverse wave, right? The form I'm talking about is
I'm just wondering, can those two terms be combined in equation 16, 117 to begin with?
they are not combined, they're separate terms. But for the form of the u that we have, it simplifies to 16, 118.
Okay. Under what condition?
This condition. So for example, the second term, Sm Laplacian of u becomes Sm times by partial 2u by partial x squared, u sub x for that matter, right?
Okay.
And then the other components are 0. So I can write it like that, 0, 0. Okay?
So, okay.
Yeah.
Only under the condition of u equals u of xt 0, 0 does that equivalence apply. Okay.
Yeah, that's why I say these are plane wave solutions. They depend only on x. Otherwise, it will not be just this term, right? The Laplacian, then you've got to add partial 2ux by partial y squared and partial 2ux by partial z squared in there.
Oh, okay.
Yeah, it's just that for longitudinal wave, for longitudinal plane wave, that's what we mean by the displacement, the distortion, if you want. And if you work out the terms, like this one is very simple. If you work out the other one, you've got to take the gradient of the divergence of u. If you work this out, you should get something that has partial 2u by partial x squared as well. Okay?
Okay. Thank you.
Yeah. All right, any more questions?
Will you still have office hours next week?
You can always send me email, or if you want to request a Zoom meeting, I can always do it.
Okay, thank you.
You know, just let me know.
Okay.
More questions, anyone? All right, if not, then good luck on your finals. It's almost the end, so you will have survived one of the more, how do I put it? Interesting chapter in your life. harder class? What do you mean by harder class?
I've heard from other professors that usually classical mechanics is one of the harder courses through your undergrad.
Really? No, I always thought that classical mechanics is conceptually the easiest. E and M is mathematically the most challenging, and quantum is conceptually the most difficult. The mathematics of it is not. It's linear algebra, but it's not that difficult. Yeah. But to me, quantum mechanics is the most interesting. Mechanics is very relatable to your everyday life because we are always talking about only either single particle, or we are thinking of solid objects that are macroscopic. So yeah, it's more intuitive because you can relate it to everyday life. Quantum mechanics is very weird, especially the parts that are very important now with, quantum computing and Chern numbers, topologic properties, and whatnot.
When it comes to electromagnetism, though, it's still treated classically, right? I mean,
Yes.
but why does, even when you treat it classically, you still have that invariance? You get the speed of light and all those. Is it just a coincidence, or?
No. Ultimately, everything that every theory that we come up with is just a model, right? And nature behaves in a particular way. So it turns out that the Maxwell equations, the way that even when you understand it at the so-called classical level, has more of the elements of nature than classical mechanics. I don't know how else to put it, but
I see. So then I'm assuming there's another theory for electromagnetism at considering relativity, right?
no, E and M is consistent with relativity.
Oh, I see.
Yeah. What people have successfully done is to combine E and M with quantum mechanics, and that is one of the most exactly experimentally verified theory. They can verify in others in lab experiments, they can verify certain quantities to more than 10 significant figures. And that is called quantum electrodynamics, QED. But even in QED, there are some very, very strange things going on. I don't know, in E and M, I mean, did you cover the part that has infinities in it that you can't really account for?
The book would have footnotes and stuff like that on those special cases, but we we didn't really cover anything on
Yeah.
infinity.
Yeah. So see, it's very interesting. That's why one of my favorite Einstein quotes is actually something to the effect, is paraphrasing, is the most what did he say now? Say the most what is it? Something to the effect that the most amazing thing about nature is that it is understandable. Because, you know, we can predict a lot of things. We can do a lot of experiments to confirm a lot of things. Like I said, QED, you know, they predict certain things. They go to the lab, they go measure it, and it's accurate to within, I mean, to more than 10 significant figures, as I said. But if you look at the theory, they have lots and lots of infinities in there that they just, you know, hide away. Well, the most understood theory, but also one of the very interesting, that they have a lot of things that they don't quite understand. Anyway, you will only get to see those courses if you go to grad school.
Those required courses in grad school, everybody has to take them, or you get to pick them?
You pick, because it depends on what you want to do, right? If you want to do like quantum field theory or particle physics, where you want to unify the different theories in physics, then something like that is a required course. Required because it's such a well understood field theory. There are not many field theories that are understood, but and you'll find that when you try to unify all the different branches of physics, you always have to use a field approach, and field approach, you would almost always talk in terms of Lagrangians. You start off from Lagrangian, then you apply the formalism and derive all the properties from your theory.
I see.
As a percentage of physicists doing this is rather low. Because other than pure theory, it's not very used, right? In applications, it's very little. But of course, the mathematics behind it can always be applied. Math can always be applied to many different areas. But it's not as clean as in physics. That's all. All right, folks, good luck, and we'll hopefully see you around in the fall, although we still don't know what form the classes will take at this time. All right, take care.